Hi everyone. In this video, we're going to continue our discussion about acceleration. Specifically, we're going to talk about acceleration constraints. So here's our problem. We can see that there is the crank with a groove that has been cut in it. The blue body, I've drawn it in blue so we can see it. It's behind the crank. It's a slider inside of a vertical groove, and this slider has a little nub that has been fit into this groove. On the top of the slider is a rope. This rope is fed over two discs. The rope then runs through a little support, and then it comes back and it attaches to the center of the big disc. And then there is this block that is strung from the support. So we're going to model three rigid bodies. We're going to model the crank, the slider, and the block. We are not going to model the two discs. Now, if we did model the two discs, we would include the masses, the inertia of the disc. We would include perhaps friction at the surface between the rope and the pulley discs. We're just going to do a simplified analysis, and we're going to omit those. So what do we want out of this problem? Let's formalize that. What we want is to derive the acceleration constraints. All right, let's think about the procedure for this problem. First thing we're going to have to do is we're going to have to do position and orientation. From there, we need to derive the constraints. And we'll just go ahead and put these together and determine and calculate degrees of freedom. Once we do that, we're going to move on to the velocity level. So let's say linear velocity, angular velocity, and the velocity constraints. And then after that, we will do linear acceleration, angular acceleration, and acceleration constraints. Okay. All right, let's, we've got this in our head. We know what we need to do. Let me clean this up, and we're going to get started with position orientation. We know that we need an inertial reference point. Let's keep it simple. Let's put the inertial point right there. Out of habit, we like to attach at least one point to every body, and since let's call the slotted crank body A, we can go ahead and put point A on this point as well. If we were doing a full dynamic analysis, we would of course need centers of mass. So we could define some center of mass in this slotted crank. We're not going to do that for this problem, so point A right here is fine. Let's say that this nub that is attached to the block, let's say that that nub is point B, and then we need some point to keep track of this other block. So what I'm going to do is I'm going to just draw a line right through this support, and I'm going to say the point at the middle of that line is going to be point C. Now, point C may not be literally attached to this block, but clearly whenever point C translates up and down, so does the block. All right, so that's good for points. We might need to create some other ones as we go through. For orientation, we're of course going to attach frames to bodies B and C. We can see in the problem that these bodies don't rotate. We're at least going to assume that body C doesn't rotate, it only translates up and down, it doesn't swing in the wind. Just for time, I'm not going to go through the formal definitions for B and C, but we do have the rotating frame attached to body A. So there is XA, there is YA, and we of course know that we need a non-moving inertial frame. So XN, YN. All right, let's go through and let's define the positions for these points. And let's say that the ones, obviously we could define any position vectors we want, and clearly point N and point A are on top of each other. So let's define point N to B, and And let's define point N to C. Now, there's a horizontal distance between N and B and N and C, and those distances do not change. So we could say the first of those distances, L1, the other one, L2. So from N to B, recognize that we could actually do two different definitions from N to B. We could say, we could go in the groove, right, and that's a changing distance. So let's say, right, so that distance, I'm just going to draw it right there. I know it's a little off. Let's call that one Q1. So we could say, all right, this is Q1 in the x hat A direction. That's a valid definition for the position of point B. We could also say, and tell you what, I'm going to do these on top of each other. We could also do L1 x hat N plus, I'm gonna take some of these things off as we go through, just to try to keep the diagram clean. We could do L1 in the horizontal, and then we could track the vertical displacement of this block using another variable, Q2. So Q2 in the y hat N. Now, Q2 is a variable, of course. I tend to always do my Q's as positives in the X and Y directions. Clearly, if this block were to drop, and it were to drop below this datum plane, the X hat N, point N, then the numerical value of Q2 can go positive. It just so happens the way we have drawn it, the value of Q2 right now, if it drops below it, it goes negative. And the way we've drawn it right now, Q2 is positive. So these are both valid definitions for point B. Next. The position vector from N to C, well, we have this horizontal distance L2, so that's L2 in the x hat N, and let's keep track of the vertical displacement of the block, and we can call that one Q3. So plus Q3 in the y hat N direction. Now there's, of course, numerous ways that you can set the problem up. We could, for example, have put point N somewhere on the top of this problem. That might be useful because we're going to eventually have to write some equations keeping track of the rope, and maybe we do that such that we're already keeping track of these lengths of the rope. That's possible as well. And one thing to consider is it even really necessary to do these two different definitions for P and to B? Well, if you're thinking ahead, we're going to have to write some constraint equations, and there's going to be a constraint that connects the rotation of this crank to the translation of the block. And in order to do that, we're going to create a vector loop. So there is a loop constraint between, we're going to go from N to B, and then we're going to go B back to A, and in doing so, we're going to come down this distance Q2, and then we're going to come back. So I've basically just gone ahead and recognized that I needed to do that and got those out here in these position vectors. So we could have all these generalized coordinates just gone ahead and identified. If you only do one of these, that just means when you get to the constraint level, you might have to create new additional generalized coordinates in order to satisfy the constraints. So, so that takes care of position. What else do we need to do? Define rotations. Well, B frame and C frame that would be attached to these bodies, they do not rotate. Of course, in a homework write-up, I want you to do all that formally. Same story for body A. We know that you would do the diagram. I'm just going to do, to save a little time, I'm going to do my shorthand. The rotation from N to A is equal to, and we're doing some simple rotation around a shared z-axis, and the angle is theta. Don't do this on a homework or exam. All right, so we've got position and rotations done. I'm going to erase the rotation. And as we go through this, let's look back over and let's just count how many generalized coordinates we have. Well, we've got this, this changing distance in the slot, Q1. It's being defined in a rotating frame A, that's the angle theta. And then we have the translation of the two blocks. So we have Q2 and we have Q3. So we have 4 generalized coordinates. We have Q1, Q2, Q3, and theta. So what about degrees of freedom? Well, from observation, what's going to happen? This crank is going to rotate. As it rotates, let's think of the angle theta as the input. As theta changes, that's going to make this slider go up and down. And also the distance from N to B is going to change. For example, when this is aligned with the x hat n, that distance is going to hit its minimum. And as it moves away from the x hat n, that distance is going to increase. So this changes, that's going to make Q1 change. It's going to also make Q2 change, right? This is moving up and down. And that's going to change the length of this rope. It's going to add or feed some rope to it. And of course, as that happens, it's going to, when it's fed through here, it's going to change the length of Q3. So just from observation, we can tell that there's going to be 1 degree of freedom. Now, observation isn't enough. We have to go back and we have to write the constraint equations, and we have to justify the 1 degree of freedom claim. So let's do that now. There's going to be a vector loop that includes point N to point B, and then we're going to come back to point N. That vector loop is going to yield 2 scalar constraint equations. Those equations will allow us to solve for Q1 and Q2 in terms of the input theta. And then of course there's the rope connecting the Q2 to the Q3. As Q2 changes, so does Q3. Let's start with the vector loop. So we can start with our point N. Consider we could, if we wanted to, we could call this vector loop A to A, right? It's the same thing. So let's say Pn to N. First of all, this distance is equal to 0. We're going to use the first definition that we had from N to B. So let's say Q1 in the x hat A direction. So that's in the slot. Next, we want to get from point B back to point N. So we're going to go down, and we're going to go down through the distance Q2. Now, before we do that, just remember, what was the other position vector that we did from N to B? We did L1 xn plus Q2 yn. Well, we need to do the reverse of that now. So the reverse then is negatives on both of these. So minus L1 x hat n and minus Q2 y hat n. And of course, in this case, Q2 is negative because we've taken the negative of the defined position vector. So that is the constraint equation. That is the vector loop. It's not the constraint equation. The constraint equation is going to be the derivative, dot product. It's going to be the dot product of this. So let's go ahead and do those dot products. Equation number 1. So this is still equal to 0. I'm going to take this vector equation. I'm going to dot it with x hat n. So this is, I'll just write it here and I'll erase it in a moment. So we're going to do Pn to n dot x hat n, right? So when we dot these with x hat n, first of all, this one's in the y hat n direction, so that one goes to 0. We're going to have Q1 cosine theta minus L1. Second equation, this is equal to 0. Of course, we're going to do Pn to n dot y hat n this time. This piece, this position vector that's in the xn, that is of course going to go to 0. And we're left now with Q1 sine theta minus Q2. So these are our constraint equations. And always remember, what are constraint equations? 2 things, very simple. A constraint equation is a scalar equation that includes generalized coordinates such that you can solve for one generalized coordinate in terms of another or in terms of some constant. All right, so here's your constraint number 1 and constraint number 2. Next, we need to define this rope. So equation number 3, first of all, we're going to say that the length of the rope is constant. So the length of the rope. Next, what is the length of the rope? So I like to go through and just call out the pieces of the rope. Let's call these pieces A's. So here's A1, A2. Now recognize that this is A3, and I specifically made this problem such that it was A3 on both sides. There are other little pieces of rope. There's a little bit of rope in contact with this disc. There's another little piece there. There's another little piece there. You can include all of those in the constraints equation. In an actual problem, it's necessary. You need to know how long of a rope to purchase or to spec. For this problem, we can omit it, and let's say that the length of the rope is equal to A1 plus A2 plus, and notice that it's 2 times A3. Now, some of these change, right? A1 and A3, those are actually changing. We could call those new generalized coordinates if we want to, or at this step, we can actually just step in and define A1 and A3, and we can take care of them and eliminate them so that we don't have to carry them through the problem. So what are we going to do? Let's say that A1, how should we define A1? A1 is this length, right? We already have a motion variable, a generalized coordinate for the block, so let's define A1 in terms of the coordinate Q2. And how are we going to do that? Well, we can come over and we can put a little kind of temporary point right here, and we can recognize that, there we go, that distance is Q2. This distance is A1, and the total distance is known. It's fixed distance from here to here. So let's say that, let's actually write the equation this way. Let's call this height, let's see, we had L1 was this one, L2 was that. Okay, so L3 is equal to what? Well, it's just these pieces, right? It's A1 plus Q2, and the difference there is just some geometry of the block. And hey, that's a fixed distance as well. So we can say that L3 is equal to, let's say, A1 plus Q2 plus L4, right? This fixed distance between these 2 points would be L4. Now, what happens if theta, right? What if this is having a negative rotation and it's in quadrant 4? That's going to bring the block down here. And we said a moment ago that Q2 is going to go negative, right? The numerical value of Q2 is going to go negative. What's going to happen? Recall that this is a constant, right? L3 is constant and L4 is constant. We could actually even rewrite this, and I can move the L4 to the other side, and it's a constant minus a constant, which just makes a different constant. So this is now L5, right? That's L3 minus L4. So here's some constant equal to A1 plus Q2. Well, if the numerical value of Q2 has gone negative, then that means, the value of A1 must have gotten even larger. And you can't see. Okay. So the numerical value of A1 has to continue increasing the more negative that Q2 gets. So that really what we're saying is that as the block continues to drop, the numerical value of Q2 becomes more negative. So the magnitude, right, this length of A1 is growing and growing. Okay. So here's our definition for A1. We can just rewrite this now. A1 equals L5 minus Q2. And of course, L5 was just that combination of constants, and it's a constant by itself. So let's just hold on to this equation for a moment. And let's take care of Q3 now. We're going to do the same thing on Q3. Notice, in fact, again, I set the problem up this way on purpose to make it easy. This vertical distance is the same thing as this vertical distance between these points. So we called that L3. So let's say L3 equals, and now it's going to be, this time, because of where we put point C, we can just combine Q3 and we can combine A3. So now it's A3 plus Q3, and we can solve for A3. So A3 is going to equal L3 minus Q3. All right. If you had called A1 and A3 additional general coordinates, so this would have been, say, Q4 and Q5, that means you would have needed 2 additional constraint equations, and that's literally what these two are. These would have been your 2 additional constraint equations. What I'm going to do is I'm just going to take these and I'm going to put them now directly into this equation, and that's going to eliminate the A1 and the A2, the A3. So the length of the rope now is equal to L5 minus Q2 plus A2 plus L3 minus Q3. Okay, and then we can erase this, and there now is our rope constraint. So just to get these things, well, I don't have to have them all lined up. It's in the video. You've got it. Okay, so there is equation 1, equation 2, equation 3. So what are we going to do at this point now that we've got the constraints? We're going to say that 4 generalized coordinates minus 3 constraint equations. This is now equal to 1 degree of freedom. So there's the justification for the degrees of freedom. All right. So what I'm going to do next, consider that the problem statement asked for the velocity constraints and the acceleration constraints. In a full dynamic analysis, we would of course define linear and angular velocities, linear and angular accelerations of all of these things. Just in the interest of time, since we're not explicitly asking for that, let's just cut right to it and let's do the velocity constraints and then the acceleration constraints. Okay, so what I'm going to do, actually, yeah, I am going to move this equation over. So here is constraint number 3. We said that L length of the rope. This is going to equal, notice that L5 and A2 and L3, oh, there's actually a, whoops. Sorry about that, there's a 2 here. So L5 and A2 and 2 times L3 is a constant, so 2 times L3 is a constant as well. You can take those and you can just add them together and they make a constant. So let's say that, what are we up to now? L6, sure. We don't have to call it a length. We could call it C, right, some constant. So here's some constant C where C equals these things. On a homework or exam, if you're going to define something new like this, you just write a little equation that says, oh, by the way, C is equal to L5 plus A2 plus 2 times L3, right? And save a little space. So you put this comment somewhere in the work, and then now we can continue forward with this constant C. So what the length of the rope is C minus Q2, and then minus 2 Q3s. All right. So that's cleaned up pretty nicely. Here are the constraints. And we want to do the velocity and acceleration constraints. So what are we going to do? These are already scalar equations. We can just take ddt of these. And let's do, tell you what, let's do them one at a time. Okay, so let's say ddt of equation number 1, well, this is equal to 0, and we're just going to take the derivative of it. Notice that Q1 and theta, these are both variables. So we need to do a product rule expansion on this. And by now, I'm expecting you're fairly well practiced with this. So I'm just going to cut to it. This is Q1 dot times cosine theta. The derivative of cosine is going to be negative sign, so negative Q Don't forget about chain rule, negative q theta dot, sine theta, and then of course the minus L1, the derivative of that is 0, right? So here is the first of your velocity constraints. So let's put these in boxes so we can keep them separated. So this is the first velocity constraint. What about that first acceleration constraint? How about the second derivative of equation number 1? Well, the left-hand side is still equal to 0, and we're going to go through and we're going to take derivatives of these now. So q1 dot is a variable, theta is a variable, q is a variable, theta dot is a variable, theta is a variable. So we're going to have to do a series of product rule expansions on each of these. We can see the first term is going to yield 2. We can see that the second term is going to yield 3. So I am just going to write these down. I expect that you can take derivatives. So q1 double dot cosine theta. Next, q1 dot times the derivative of cosine. Well, we know that's negative sine, so negative q1 dot theta dot sine theta, chain rule. We're going to take the derivative of this next one. This time we have minus q dot theta dot sine theta. Next, it's going to be the ddt of the theta dot, so minus q theta double dot sine theta. And then now we need to take the derivative of sine theta. That's going to be cosine theta. Don't forget about chain rule. And we're going to have minus q theta dot squared cosine theta. And of course, you look at these terms, you see that we can actually collect some terms. Notice that these are the same, so we can combine these, and this is minus 2. All right. This should start to look familiar. If you recall, we did linear acceleration in the previous video, and we said that there were 4 types of linear acceleration that can come out of this. If you have a position vector that is changing distance and is rotating, then you're going to have slip. There's the slip component. You're going to have tangential. That's your theta double dot. You're going to have a normal component. There's your theta dot squared. And then the fourth one was the Coriolis term. And there it is, 2 times q1 dot theta dot sine theta. What we have effectively done, consider that we did the dot products first. We could have taken the vector loop and we could have differentiated the vector loop. And what would have come out of that if we had? We would have had a slip and a tangential and a normal and a Coriolis going from point A to point B. And then we would have this position vector, right, from point B down to well, this point on the way back. And there's going to be some component here, right, the Q2, and clearly this is slipping in the groove, so there's going to be some slip acceleration there. Now, we don't see that in this first equation because consider what we've done is we took the dot products, and this is just the accelerations in the x direction. Well, this component, the q, right, there is no q dot or q double dot in the vertical direction, so that's why it doesn't appear in this equation. Now, what is going to happen when we come in and we take derivatives of the second constraint equation? So ddt of number 2, here is the second velocity constraint. ddt of theta 2, or equation 2. Well, q1 and sine theta, q1 and theta are variables, so we're going to do product rule expansion. And this time, when we take derivative of q2, well, q2 is a variable as well. So we're going to have q1 dot sine theta. Derivative of sine is cosine, so plus q theta dot cosine theta. Again, chain rule. And then we're going to have minus q2 dot. And of course, we could have taken the original vector loop and we could have differentiated it on that level, and then we could have done dot products and we'll get the same answer. Let's take the derivative of this one now. ddt, so this is d squared ddt squared, dt squared, so of equation number 2, the left-hand side is of course still equal to 0. And what is going to happen now, hopefully you can see where this is going. We're going to take, we're going to do a product rule expansion on this one. We're going to do a product rule expansion on this one. The first one's going to yield 2 terms. The second one is going to have 3 terms. And the form of these are going to be very similar to what we had last time. So this is q1 double dot sine theta plus, actually it's going to be minus now, derivative of sine is, or no, still plus, sorry, cosine, plus q1 dot theta dot cosine theta plus. Now, what's going to happen when we take the derivative of this one? The first term is going to be ddt of the q, so that's going to be q1 dot theta dot cosine theta. That's our Coriolis term. So we can go ahead and combine those. Plus 2 q dot, that's q1 dot theta dot cosine theta. So that was the first term out of this this triple product rule expansion. So that takes care of the q dot. So next, plus q theta double dot cosine theta. And of course, we take the derivative of cosine, we get negative sine. So negative q theta dot squared sine theta. And we still have this slip velocity, so this becomes a slip acceleration. q2 double dot. Okay, so here was the second velocity constraint. Here's the second acceleration constraint. And just like we said last time, you don't have to do the dot products first. You could have differentiated this twice and then taken dot products. You get exactly the same thing. Next. That takes care of the vector loops. How about this rope constraint? Well, the left-hand side is the length of the rope, which is constant. We take the derivative of that, we get 0. Here's the other constant. Derivative of that is 0. So negative q2 dot minus 2 q3 dot. Now this one is best represented, I think, by just moving one of these to the other side. So let's say that q2 dot is equal to negative 2 q3 dot. And what does this mean? We could, for example, let's say we want to solve for the q3. So let's actually move the negative 2 to the other side. And we get a negative 1/2, right? So q3 dot is equal to negative 1/2 q2 dot. We defined q2 and q3 such that they're positive in the positive y-headed directions. So this is telling us that if you take a q2 dot and you put a negative 1/2 on it, you're going to get the q3 dot. So does that check? What happens when q2 dot is positive? When q2 dot is positive, then this block is going up, right? This block is going up. This equation tells us that when block B is going up, block C is going down. And the fact that the rope has been run through the support and come back up means, suppose this one goes up 1 foot. That means there's an extra foot of rope at the end of this whole process. And since it has been doubled up, you end up with 6 inches on the left and 6 inches on the right. So the speed is only half. the speed of the block is half of the speed of the slider. And of course, we can take the derivative once more. We can say that d squared over dt squared of equation 3. And I'm just going to take the derivative of the rearranged version. So q3 double dot. It's a very ugly double dot. Double dot. This is going to equal negative 1/2 of q2 double dot. So we said we wanted velocity constraints. Here they are. We said we wanted acceleration constraints. There they are. All right. This is basically wrapping up, right? This is the final topic we had in our kinematics section. At this point, what I expect from you is that if I specify a point on the problem and I ask you for the linear acceleration of that point, you can tell me. You make a position vector to the point and you differentiate it twice. If I ask you for the angular acceleration of a body, you should be able to tell me. If I ask you for the velocity or acceleration constraints, you should be able to tell me. Now, the purpose of this, right? What's the whole point of these, right? The purpose of the constraints is that it allows us to solve for dependent coordinates, speeds, accelerations in terms of independent. So, if we needed to know the acceleration of the block C, we could define that in terms of the acceleration of block B, which we could in turn define in terms of the acceleration, the angular acceleration of the input crank. So if you control this variable, you control all of the other variables. Okay, so that's it for this video. If you have concerns or anything, let me know, but I will see you later. Best of luck.